Okay, so we're going to have a look at how these different radioactive particles are formed in the nucleus. We're going to start with alpha, and what we notice with where alphas are formed is that they form generally in our much bigger nuclei that are much more unstable. It turns out that alpha, like a helium nucleus, is a little packet of stability, like it's a really stable nucleus. And so if you've got a really big, unstable nucleus, it's very easy for two protons and two neutrons to kind of clump together on the side of that nucleus and then get repelled away by the positive charge in the nucleus and the positive charge on the alpha particle. So we're talking like a big nucleus. And then what happens is that two protons and two neutrons will clump together on the edge of that nucleus. And so we've got positive charge in the nucleus and positive charge on the alpha particle. And so we're going to have an electric force pushing that little clump of particles away. And they'll tend to stay clumped together because helium is a really stable nucleus to form. And so this is what's giving our alpha particles their kinetic energy, is that they're being repelled away. It's that, we call it Coulomb repulsion, Coulomb being the unit for electric charge. And so the electric force, aka the Coulomb repulsion, is acting on both the big nucleus and on our little clump of two protons and two neutrons, and it's repelling those away, giving them their speed, which often comes out at 10% the speed of light. That leaves both the new alpha particle and the original big nucleus more stable. So big nuclei, as we start to get really big nuclei, we've got lots of protons, and to keep all those protons together when they're trying to force themselves apart, because they're all positively charged, we need to have neutrons in there which exert a force that holds the protons together even though they're pushing apart. But as we get more and more protons, they're pushing each other apart with more and more force, and so we need more and more and more and more neutrons, and the whole thing gets quite naturally unstable. And so by breaking off two protons and two neutrons, we're decreasing the number of protons more than the number of neutrons, because if we look at our big elements, they've all got way more neutrons than what they have protons. And so if we take away two of each, the ratio of protons to neutrons is decreasing, even though we've taken away the same number of each. And that leaves our big nucleus more stable. Fewer protons trying to push the nucleus apart. And so both nuclei end up more stable. The beta minus, we're only going to talk about beta minus emission. And beta minus emission, we see it happening in nuclei that have too many to be stable neutrons. And so what happens in the nucleus is we have a neutron that decays to form a 0, -1 beta, an electron, plus a proton. And so in the course of this reaction, a lot of energy is going to be released. You're going to have the mass of the new nucleus is going to be less than the mass of the old nucleus, and so that change in mass is going to be converted into kinetic energy of the beta particle, and so it's going to be emitted from the nucleus with lots of kinetic energy. It's not possible for electrons to exist in the nucleus because of the uncertainty principle. The nucleus is so tiny that if we confine an electron to be in the space of a nucleus by restricting the space it can be in to be so tiny, that means that the speed it's travelling must be very fast. And so as soon as this happens, as soon as a neutron in the nucleus decays to make a proton by releasing a beta, immediately that beta has to be emitted from the nucleus.
Hey man, I'm trying to do physics.
So gamma particles are released after another particle has been released. What happens is that if we think back to our beta emission, where a neutron decays into a proton by releasing an electron, that's going to leave all of our nucleons inside the nucleus a bit kind of shaken up, because one of them that used to be a neutron has suddenly turned into a proton, and so it could easily be sitting right bang next to another proton in the nucleus, and they're going to be pushing each other apart. They don't want to be right next to each other, and so what's going to happen in the nucleus is that the nucleons are going to rearrange themselves. They're going to kind of move around, kind of click around like a Rubik's Cube, kind of clicking around to a new formation that's more stable, and because it's more stable, that new nucleus is going to have a slightly smaller mass than the old nucleus, and that difference in mass is going to be released as energy. That energy is released in the form of like a photon that comes out of the nucleus. So, nucleus is unstable after the previous emission. The nucleons rearrange themselves to be more stable. By becoming more stable, they have less mass. Kind of happens, if you think about standing on a chair, you're not very stable. As you fall to the ground, you're in a position of greater stability, and so energy is released. We have to account for that release of energy. Somehow, where did that energy come from? We see that it comes from the mass of the nucleus decreasing as it becomes more stable, because the forces acting in the nucleus are such big forces, like they're way bigger than gravitational forces. We're talking like electric charges. Just rearranging the neutrons can release enough energy to be like a measurable amount of mass difference.
But, so when the neutron decays, it decays into a electron and a proton.
Yeah.
The proton remains inside the nucleus.
Yeah.
And the electron leaves.
Yeah.
The electron has no mass.
Electrons have mass.
They just
so
have really
it's
small
changing
mass.
that electron's mass.
No. If you measure the mass of a neutron, and then you go and measure the mass of the proton,